We're asked to find the minimum distance of the point 0,2 from the point 0,2 to the curve y equals x squared. Now, just intuitively, we can see that some points on this curve are closer to 0,2 than others. So we can draw an approximation. If we move over to this thing, it's what looks kind of like a perpendicular maybe. We get a point that looks like it might be the point of closest approach. It doesn't prove anything, but it looks like that point occurs between x equals 1 and x equals 2. For x equals something between around 1.1 or 1.2, probably around 1.2. Now I'll say that there are 2 points. If this point works, and the note here says it's got a question mark, is this the minimum distance of the curve from 0 to? Is this line here the minimum distance? Does the minimum distance occur between this point and this point? Okay, well, maybe it could. One thing we do want to note is, due to the symmetry of the curve, if this point works, then this point directly across from it on the curve has to also work. So, then it's a little hard to read that. That just says this one works if that one does. Okay, so now to set the problem up, to figure out the minimum distance, we have to have a mathematical expression to minimize. So what we want to do is we want to take a point xy on this graph, and we want to figure out the distance from 0,2 to the point xy. It's a good place to start. So we draw our fundamental triangle. Our fundamental triangle has legs y minus 2 and x minus 0, so that well, from the triangle we can determine that the slope is this. We don't need that, but there's the slope. And we can determine more to the point that the hypotenuse is this, the square root of this squared plus this squared. And that is the distance between 0,2 and the point xy. Now we can also note that since the y-coordinate of this point, since the x-coordinate is x, the y-coordinate has to be x squared. So that the expression we have for the hypotenuse, x squared, square root of quantity x squared plus quantity y minus 2 quantity squared. Since y equals x squared, that becomes square root of x squared plus quantity x squared minus 2 quantity squared. We want to minimize the distance. We want to minimize then this expression. If we can minimize this expression, then we know the x-coordinate of the point that gives us the minimum distance, and we can plug that in to y equals x squared and find the y-coordinate. And we can also evaluate this expression to determine what the minimum distance is. Okay, so we could find the minimum of this function, but using critical points and first or second derivative tests. But that function is a little more complicated than we might like. Not that we couldn't handle it, but it's a composite that includes inside of it another composite. If we just got rid of the square root, we could minimize that expression much more easily, and that's going to work fine because what's under the square root is always positive. For any x value, this is going to be positive. And if we minimize what's inside, we minimize its square root. So, distance is minimum if and only if the distance squared is minimum. So we minimize x squared plus quantity x squared minus 2 squared. Okay, so we minimize it. We let f of x equal x squared plus quantity x squared minus 2 squared. And we can expand that. We get x to the fourth minus 3x squared plus 4 when we expand the binomial, square the binomial, and add the x squared. So that our derivative f prime of x is very easily found. Once this is expanded, the derivatives are very easy, and I'm not going to read them to you. You can verify that these are the correct derivatives. And now the critical points. What are the critical points? Critical points occur when f prime of x equals 0, so we set the f prime of x expression equal to 0. And we solve it, and it's easily solved. We get either x equals 0 or x equals plus or minus the square root of 3/2. Now, when x equals 0, we're going to do a second derivative test. We got the second derivative. It's going to be very easy to evaluate it at x equals 0, negative square root of 3/2 and square root of 3/2. At x equals 0, we can easily verify that the second derivative has value negative 6. Meaning that at that critical point at x equals 0, we have a relative maximum. The negative second derivative means we have a downward concavity at the critical point, so the critical point is sitting at the top of something that looks at least somewhat parabolic. Okay. Now, at negative 3/2 or at positive 3/2, we're squaring x. It doesn't matter which one we square. We get x squared equals 3/2, and 3/2 of 12 is 18. Subtract 6, we get 12. Looks like I subtracted 6 and got 6 instead of 12. Let's fix that. Note that we don't really have to get the exact value of f double prime of x. In some cases, it's easy to tell whether f double prime of x is positive or negative. And in this case, clearly, since x squared is going to be bigger than 1, this is going to be bigger than the negative 6. Not to excuse the fact that I did evaluate it and got it incorrect, but this doesn't change our conclusion because 12 is positive, as is 6. So the main thing is f double prime of x is positive, and that gives us a relative minimum at each of these points. Okay, well, we can evaluate the square root of 3 over 2. It's the square root of 1.5. It's about 1.223 or something like that. Pretty close to 1.2, which is what this point looked like. Okay, so that kind of confirms our graph and kind of also tends to give us some confidence in our solution. Also, our x equals 0 point gives us a relative maximum. We don't have room to draw this out, so I'm not going to draw the graph. But what happens is, as we go from here to here, the distance continues to increase. But once we pass the origin, the distance starts decreasing toward our other minimum over here. Because remember, if this is a minimum point, this is also a minimum point because of the symmetry. So as we move away from the point going this way, our distance increases till we get here, then decreases, and we do have a relative maximum at this point, and that's confirmed by our analysis. Okay, in any case, distance is a minimum for x equals plus or minus square root of 3/2. We could plug that plus or minus, well, square root of 3/2 in for x here and actually get our minimum distance. It looks like that minimum distance is going to be something like around 1.3 maybe. But it'd be interesting for you to plug that in and see how close I came with my guess. And I'll note that I didn't come all that close. It's a little more than that.